Yeah.
Morning. So we're going to continue our discussion on algorithm strategies. Not a lot to say on this. You'll see. But before I start, I wanted to ask a question about how the problem set for week is going. Near there? What? Someone work problem. Oh, it's a problem. I heard problem, but I didn't hear threat. Okay, well, I do have to ask you something about when you prefer to have. Sorry. Yeah. So a quiz is coming up, right? My quiz is going to be on your master theorem and analyzing algorithms, which is what quiz one is supposed to be about. I need to set a date and time. Now, you don't need more than an hour to do it. Yeah, it's online. There's a practice quiz that is very similar, already available. You've seen it? Yes. Have you tried it? It's locked? Yeah. Last year. Oh, it was a real one? No. That's an accident. I actually meant for that to be open perpetually. So I thought it was already available, which is why it's busy. The quiz is waiting to become visible once you've set a date. Now, how it works is I typically open it somewhere between 24 and 36 hours. What we just need to agree on is which period of time you'd like for that to be. You don't need more than an hour to do it, I don't think, but you don't get more than an hour to do it. Doesn't matter. And so, with respect to people who may be Sabbath observers, and therefore Saturday might be an issue, as well as perhaps Friday evening. Sorry? Right. Exactly. So you're watching one point. The point is that I want to open it for a 24 to 36 hour period, but it's up to you whether you want it in school time, Thursday to Friday, or you want it Friday to Sunday. What? I think we get two. You get two of them. Alright. So it's gonna be a weekend, Friday and Sunday. And then, alright, so originally I was wondering whether you need an assignment with it, but I think it's so short you can do it anyway. Meaning this shouldn't interfere with your doing the problem set. Anyway. So this is not becoming Friday and Sunday. It's not becoming Friday and Sunday. It's okay? So it's not that this is for next week, it's for the following week. And so I guess, okay, so here's the thing. So Friday and Sundays will have time proposing set for it, but a lot of people don't like that. You should put that on the discussion board. If anything, what I can do is perhaps start a posting and respond to it there. And we can see what the majority feels. If it's in the week, it's going to be a 24-hour period. If If it's on a weekend, then you get the 36 over. Because of the difference, people have a Saturday working. Alright. So this is week of sorry. No, not like that. Today is 16th, 23rd, so 26th to the 30th of February. March 28th. It's not a leap year, so. In other words, so February 29th this year is March 1st. Right? So in there we'll have a quiz. Nominally for now. It's going to be Friday. Sunday, I guess that would be March 2 to March 4. Okay? So unless for some reason we decide to override that. Okay, question? All right, so let's go back to the actual content. If you recall, last class I left off with a discussion on dynamic programming, and I've mentioned to you, look, dynamic programming is basically like you're doing your divide and conquer, but you're caching your results. So you don't repeat the computation that you already have the answer to. And then I mentioned to you that the general way of solving the problem is to proceed bottom up. I didn't actually show you the table that one would build for the coin change problem. You can look it up. It's not that hard to see once you understand what's going on, once you get that recurrence that I showed you on Tuesday. But I've been a new. If there's time at the end of showing these, I'll go back and show you that table. But like I said, it's a famous problem that you can see. And remember, dynamic programming itself is not a topic that specifically you need to master. For this course, my job here in exposing it to you is really to let you be aware that there is this thing called dynamic programming has that topic. Now, moving on. So, read the algorithms. Try to locally optimize. So, something is called greedy if you select a locally optimal choice in the whole. That it leads to globally optimal solution. In the whole. Yeah. In other words, it doesn't always do that. Now, in some cases, it does. And in many instances, it kind of depends on what you optimize locally. So you can sometimes find a very clever thing to optimize locally that actually does lead to a globally optimal solution. Later on, we're going to do an algorithm called Dijkstra's algorithm for finding shortest path on a graph. And that's actually an example of a kind of greedy strategy because you can make some locally best choices. And it turns out that those locally best choices are provably going to lead to the best choice overall. That's an algorithm for solving the shortest path on a graph. And if at every step of the way you take the next best step you can, you will eventually get the shortest path. So that's an example of a greedy algorithm but it's not stupid reading. It's very clever and careful reading. So reading, just because it says the reading strategy, and just because I use the word hope here, I know I make it sound like this is futile and you probably shouldn't be using it. But the idea about a reading strategy is that typically not too hard to implement, and it's just fairly efficient if you can, if those locally optimal choices are easy to complete and lead to two choices. But it can have some spectacular failures as well. So, let me give you an example. So this doesn't, so when it works, it's good. It's often simple. To implement. But it can be wrong. So here's an example of a problem. Have you ever heard of the knapsack problem? They're not seeing anything? It's worse. You want to start the phone?
Tell you what, I can stop it and then
start the phone and just no, make my phone join the meeting.
Oh.
Right. Just look at the meetings happening, you stopped it.
What's recording now? Okay.
Oh, okay.
So you can see the board now.
Sorry, it's a knapsack problem. Knapsack problem is basically you're given a set of objects. And you have a knapsack, you're trying to pick up objects and put them into that knapsack. Each object has a given weight and a value. But your knapsack has a capacity. So you're given a knapsack with a capacity C. And you're also given objects so, well, all right, let's say it like this. W1, E1 to Wn, En. Where each W is the weight of the object and B is the value. And what you're trying to do is maximize the value subject to the constraint that some of the weights must exceed the capacity. Right? So you have a bunch of objects on the floor. One of the stories that they will tell is, a thief breaks into let's say it's a store. And this bag is only so big, the objects that are lying around for him to take all have different weights, but also different values. What he's trying to do is maximize the value of the root of all, the root, but that can still fit in the bag because he needs to close it. So what you want is you want to find maximize. All right, so find a subset of the objects such that some of the weights is at most the capacity, the weights don't exceed the capacity, and some of the values is maximum. All right, that's a famous problem in that it's known to be hard. Now, if you try a greedy strategy on it, it doesn't always work. And actually, what's interesting here is it depends on what you are being greedy on. So, if you choose to be greedy on the value, so you go in there and say, okay, grab the most valuable thing first, and then, you know, whatever space you have left, grab the next most valuable thing that will fit in that space, and so on until you can't hold anymore, and then leave. Well, that turns out, I mean, that sounds like a natural thing to try, right? That turns out not to always give you the best answer. So let me give you an example, and this is why I made sure I'm bringing this with me, because making up an example that actually works takes a little doing. So greedy doesn't always work from that side. So here's an example. Suppose your initial set of objects had the following weights and values. 5, 6, 3, 4, 3, 5, and 4, 3. All right, so greedy says, oh, my laptop, what's in there? Greedy says, if you're being greedy on the value, greedy says, take the one that is most valuable. First. Oh, what's the capacity? Capacity was, just make sure I get this right. Capacity is, capacity is 10. Good. So what will greedy do? Greedy says, take the one that's most valuable first. So then that means to taking item 1. So greedy will take item 1 first. And of course, the capacity left over is 5. And so the next thing that's most valuable after that 6 is, oh, this 3, 5 here, right? Which fits. So we'll take the 3, 5 next. Now at this point, the total capacity it's used up is 8. You notice that I can't take the 3, 4, I can't take the 4, 3, so I have to stop right there. So for a total value of 11, 6 plus 5. Yes? But what's the best way to do it? You could have done better by taking the 3, the 3, and the 4, because the total value would have been 3 plus 5 plus 4, which is 12. So the actual optimum would have been all the others. For the value of 12. So here, you get a better value than the greedy strategy. So of course the greedy gave you the wrong answer. But it was fairly easy to do. What you took on each step. So that was first, this was second. What you took on each step was fairly easy to decide. Okay? Any questions on this greedy strategy? Remember, it's not an algorithm, right? It's a whole family of algorithms. And by the way, these families are not mutually exclusive. So it's possible for you to have an algorithm that is both a backtracking as well as greedy. Or that uses a divide and conquer approach and is taking a greedy approach internally within the recursive calls. Okay, any questions? So let's look at the next one. Question? The capacity is a value. You know what capacity means? It's a limit. Don't exceed it. Sorry? Yeah, the value is 11 because the sum of the values is 6 and 5, right? So the total value is 11. The capacity is something you must exceed. And the weights were 5 and 3, 8, which don't exceed 10. Which is why we couldn't check anymore because the capacity was 10. The capacity is a limit. Capacity is how much a bag can hold. How much make the bag full? That's what capacity means. So you can't exceed that because that is a limit on what items you can take. Okay? So that was what prevented you from taking any more. Because once you got to 8, you couldn't take any other items without exceeding 10. Okay. No other question? Still? No. Question was, is the reason that this is optimal because I reached 10 as my total weight? No, that's not the reason it's optimal. The reason it's optimal is because the value is the highest you could possibly get. 12. Within that capacity, correct. Okay. Yeah, so to put a finer point on that question, it is possible for you to have an optimal value without actually reaching the capacity. Right? Okay. I'm going to try and one more try with this marker. All right, so what's backtracking? So backtracking is actually a term that's used typically to represent or describe a kind of search. But if you think about it, actually, it's almost any kind of implementation that you implement recursive, any kind of search that you implement recursive. All right, so typically you have some state. Let me give you an example. Suppose you try to write a program to play tic-tac-toe. What? Use another example. Why? Yo, bad memories? I almost gave it up to myself. Right, so it's too easy. You've done it already. Well, anyway, looking for you, that's not going to end up something. So, a tic-tac-toe game is very simple, right? You could imagine, suppose I gave you a start configuration. In other words, the board looks a certain way. X has played first, O is playing second, of course. And you have a particular configuration of board, and then you want to know, is it possible for X to win from this particular configuration? So that's essentially a kind of search. And so what you'll often have is, you'll have a state, and then you'll have some operator for generating the next possible state. In this case, it would be make a move for X. That would be, in this example, how to make the next state. And what you'll be examining is, as you proceed from one state to the next, you're looking for a goal state, in this case, X winning. But as you explore and either don't find X winning, maybe O wins, you will perhaps have to, having made some tries, come back to a state and try a different option. Okay? And once you have to do that, then that's backtracking. So let me draw a picture for example, as an example. Suppose we're trying to figure out, we're looking for winning states for X in tic-tac-toe. And let's say that I start from a configuration that has maybe X here, and O here, and O. Let's say O is stupid. O plays there. So the set of next possible moves, if it's X's turn, it would be X's turn, but X plays first. You generate, here's one move that looks like, I'm going to put the new moves in purple. So here, let's put this back in black. One possible move might be place an X here. Okay? An alternative would be place an X here. Sorry? That's not working for X. I know, you know that because you're looking ahead. But the computer doesn't know that from here. Right? You can't tell. So the point is, you now need to explore all the possible next states. And for each next state, you need to continue exploring. Of course, next state will be O's turn to play. And then you try all the possible moves O could make, and then you try all the possible moves X could make, and so on. And of course, if you get to a state in which O wins, then you don't need to proceed any further. The game is over, you stop. And what you're essentially doing is backtracking to the previous choice you made. That's why it's called backtracking. So you can see where in both of these scenarios, so lots of children. In fact, anybody that's astute enough to tell me how many children of this state? 5. Good. That means you understand. Great. How many children a child would be the next possible move? How many possible places are there for X to play in this move, in this setup? There's 5 different locations that X could make a move. So there are going to be 5 children. I hope you regret not getting this question now. Because it is easier than you thought, right? Maybe the last one that you check is that one. Now, notice that each of them will have children, right? So, there'll be, how many children from this? 4, yeah. And maybe one of those children will have O playing here. At that point, you test and realize O wins. So therefore, this is a bad choice to make, right? But how does that process work, from this state, you'd have generated each of these next states in order. But you generate this one first, and then you explore from here, and eventually you discover that O wins. So you back up and try another option. Now, once O wins, technically, O doesn't need to find another play. So if you're doing this right, you'd actually, it's like you treat the levels in pairs, because X gets to move, then O gets to move. And so, in fact, once you see O winning down here, you'd say, well, X shouldn't make this play. Since you're trying to decide what X should do, you'd immediately abandon the rest of the search and come back. But I'm getting ahead of myself. The point at this point is just describing the backtracking process. You can see how it's backtracking, because what we're doing is searching through all this tree of possibilities. And why it's called backtracking is that I will later on in my computation consider what if I made a different move from the original state. So what I've done is backtracked to this previous state to make a different choice. Clear? Any questions? Any algorithm that does that sort of exploration is a backtracking algorithm. So last one then. By the way, when you move on to AI in third year, you'll see that there's actually a special algorithm for two-player games called Minimax algorithm. Why? All right. Don't worry, this is the only course where you don't have a choice whether I teach you or not. You have to do AI, but I'm not a lecturer for that. So there's an algorithm called the Minimax algorithm, and it is actually especially implemented for two-player games. And how it works is you would have a way to score the configuration. So it's called a valuation function. And that's what basically assigns a numerical value to a particular configuration. And you'll decide when you define that valuation function, which side is which. So typically, big numbers mean it's good for one player, and very low numbers means it's good for the other player. And so that's why it's called a minimax, because one side is trying to maximize that value, the other side is trying to minimize that value. And so the way that you're going to make the move, you're going to decide, you know that, say, for example, X was trying to maximize, then X wants to choose the option among his 5 choices, the one that has the largest valuation score. But the way that he applies that score is not just on the basis of this single state by itself. What he's going to do is say, well, I know that O would have played the best that O could do from this state. So if O can produce a really good move for O, this valuation, the valuation of this state is going to be very small, a very tiny number. And so, of course, when X sees this number, it's going to say, oh, that's a very small number. It's trying to maximize among its children. It's going to ignore that option. Okay? Anyway, if you didn't understand that, don't worry. You have ample opportunity when you get to it in AI. But that algorithm is called the Minimax algorithm. It's just a refinement on the backtracking idea. But it leads into this general notion of, obviously, if I have to do this naively, I'm going to explore a lot of states in general. You see that, right? For example, how many different states do I have in simple tic-tac-toe, ordinary tic-tac-toe? How much? 9. Almost have 9 on the board. A lot. 81, more than that. 2 to the 9, more than that. 9 factorial, not so bad. Whoever said 2 to the 9 was on the right track, but you forgot that there's 3 possibilities for each square. It's not just X and O, you also have blank. So you have 3 to the 9 possibilities, right? So yeah, so 3 to the 9 different possibilities. So if you just have a straight up backtracking, if you're trying to count possibilities, count number of ways somebody can win, you're going to explore 3 to the 9 different possibilities. Of course, if you're on a slightly bigger board, it gets exponentially more expensive. So straight backtracking is typically very expensive. So what do you want to do? So minimax is an example of trying to curtail some of that search. Branch and bound is a kind of generalized way of trying to curtail some of that search. So what's the idea? If I can come up with a way of estimating what the cost is to the goal state that I'm looking for. So for games like tic-tac-toe, that may not be great. I may not have a good way of doing that. But in some situations, depending on what I'm searching, I may have a very good way of doing that. Say, for example, if I'm trying to figure out, am I getting closer to a target or not? So if I do, then I have a function called a utility function that gives me an estimate of how far away I am from the goal state. And of course, using my utility function, and of course sometimes I might have a cost function, I can then decide what's the best option for me to take. So a good example of that might be, okay, do you remember the question from tutorial where we're counting the number of branches in a tree whose sum was totaling less than 100. Remember that? Okay. Now, in our implementation, we didn't do anything fancy. What we did was carry on until we got to a leaf, computed that, looked at what that sum was, and if it was less than 100, added 1 to our tally. Right? And if it wasn't, we added 0 to the tally. That would have been an example of a kind of backtracking approach to solving that problem. But we could have curtailed some of that search. How? Suppose the first 2 nodes added up to 120. Do I need to keep exploring its children? Exactly, because once you're told that the tree was a tree of positive numbers, so once you've exceeded that 100, you know that none of those paths that stem from that node could possibly be counted. Yes? Okay, so that's an example of a branch and bound approach to that problem. Because in that case, you can bound what the total is going to be, and you know it's not going to be in the range that you're looking for. It's outside of the scope of the goal state. Okay, so that's an example of branch and bound. So, I mean, actually, let's call it a search. It doesn't have to be any search. So it could be a backtrack. So you typically will have something called a utility function. And sometimes you may have something called a cost function. So that's basically how branch and bound works. You're basically limiting the set of states you're going to explore by making some kind of observation that you can about how far or whether it's possible to see a goal state that you're interested in from the state that you are at. The whole idea is to reduce the number of nodes or states that you're going to explore. Any questions on that? Yes. Yes.
I believe you said it's not backtracking algorithm. When you set bold amount of input.
Bold amount, not amount. You asked, what's the question?
So you said you gave an example of branch and bounds in backtracking algorithm. The example on the tic-tac-toe when you ask for suppose amount of moves that the person can do.
Okay.
For example.
Yes, but that wasn't an example of branch and bound. That was an example of reducing the number of states.
I'm saying so like for example, you want to explore the game, but at the beginning of the know how to make a move, so you just assume I'm going to say the first person going to move the person plays X or X.
I'm not even sure what the question is at this point. Let me try and help out a little bit though, because I don't want you to confuse the tic-tac-toe example with the branch and bound discussion. What I was trying to point out is that when you do the tic-tac-toe in the context of backtracking, with a tic-tac-toe board, you're exploring the possibilities. So if you start with a blank board, that just means that that state has 9 children, and X can play in any one of the 9 spots. And then each state from there is going to then proceed to have multiple more children, one child less than its parent, because you'll have one space less, and you'll be XO alternating. But the whole point of pointing out how many states there are is that you're going to have potentially lots and lots of states to explore, right? And what we want to do is enable. So if I just did it without nothing more, no thoughts, just straight explore according to the rules of tic-tac-toe, I'm going to explore a lot of states because I'm going through a tree like that. But what I was pointing out is that sometimes there are ways we can reduce the number of states that we're actually looking at. Okay? And I gave an example of the minimax algorithm being able to prune off, it's actually a variant of the minimax, being able to prune off this branch, for example, once we discover that O could play here and win. If I discover that first, then I wouldn't need to proceed with the others, and I could immediately kill this branch and explore some others. So that's an example of pruning the search. Now, branch and bound is a method of pruning that search, but that uses a way of measuring or estimating how far where you're trying to go is from where you are. And the example I used for that is definitely branch and bound, was for the tutorial. The problem for the tutorial, I don't know if that's what you're trying to remember. The problem for the tutorial had paths in a tree. A tree only had positive numbers in it. You wanted to count all the paths that summed to less than 100. And the point there is that you're essentially bounding, your target is sums that don't exceed 100. So if your current sum already exceeds 100, there's no point continuing down that path. And so you can prove that search by basically ignoring those children that will lead to adding more to that sum. That would be an example of a branch and bound approach to solving a problem. You can see that's going faster because we wouldn't be exploring all these paths that are not necessary. And you discover we're not necessary from early. Does that answer your question?
Yes.
Okay. Are there any other questions? Okay, so in the last minute, are there any questions on the problem set? Is this the last one? What is about easily? I didn't hear that question. Last week was easy week. This week was the hard one. Yes. No surprise. Are we going to manage on a pro? Are we going on? No. That's all the truth said. Sorry? What? Can I have one? Not here. What's the question? Why would you do that? I was trying to do our keep off on something. No. You're asking my answer. I don't know. There's lots of questions because you don't know what to say. All right, so see you on Monday.